All right, so remember, based on what I just said, your first step is to analyze your angles. I've got three different types of angles here, right? Beta, negative beta, pi halves minus beta. It's probably easier to put them all in terms of beta. So the cofunction identities really stick out like a sore thumb, if a sore thumb were to stick out, right? Because you see the pi halves minus beta. So what's the cofunction of tangent? Cotangent. And what's the complement of pi halves minus beta? Beta, right? So tangent of pi halves minus beta is just cotangent of beta, and the negative's still out there. Cosecant of negative beta. Cosecant is what? Even or odd? Still odd, right? So the negative comes out front. Now, I think I mentioned this yesterday. If you just put it out front like that, how you doing? Not good, because you've turned multiplication into subtraction. And you don't even want to put a dot negative, because that's Morse code, right? So what you do is you put parentheses there. All right, now it's multiplication. And then in the bottom, the angle's already beta, so we can kind of look to do something else with it. And of course, cotangent squared plus 1 is straight up baby PID number 2. It's equal to cosecant squared. All right. Now we can simplify from there. We have a negative times a negative. What's a negative times a negative? A positive. So I could just drop those negatives. And I get cotangent of beta. And now notice I have a cosecant factor in the top and a cosecant factor in the bottom. So if you wanted to, you could gently divide this one out and then get rid of one of those there, right? But you got to be careful when you're just slashing out powers. If you want to put like a replacement power there, you could. Like if that were cubed, you want to slash out the 2 and 3 and put a 2 there. But I'm left with the cosecant in the bottom. All right. And whenever you divide something out or draw a line through it, just make sure I can still see what was underneath it originally. All right, now at this point, we've got it down to a simple ratio, but our goal is to get it down to a single trig function of a single power. And if you're not sure what to do, right, if it's not already in terms of sine and cosine, remember that's the strategy. So that's what I would do next. Let's put everything in terms of sine and cosine. So the ratio identity says cotangent is cosine over sine. And then that's all over, keep track of the main division bar, cosecant is 1 over sine. Now, you could do stay, change, flip here, right? Stay, change, flip would require a whole nother line to write stay, change, flip, and then the final line. Stay, change, flip doesn't always work, though. But guess what does always work when you have a complex fraction? Lick them over lick them. So because I've already done stay, change, flip on previous examples, I'm going to do lick them over lick them here. I have 2 miniature denominators, sine of beta. So I'm going to multiply the top by sine of beta and the bottom by sine of beta. Remember, this is upstairs, downstairs problem, and you give everybody bunk beds. Remember that? Now, there's nothing to distribute here. It's just one factor in the top, one factor in the bottom. So we're left with cosine of beta. And in the bottom, we're left with what? 1. So we're left with cosine over 1, which is just what? Cosine. Now, as I said in the very beginning, it's probably better to put cosine over 1 and then cosine, but I'm not going to require you to go to that extent. Okay, if you're ever multiplying by 1 or you're ever adding 0 or dividing by 1, you don't have to show that step. You can go straight to your final answer. So that saves one line of writing when you do lick them over lick them. But if you like to do stay, change, flip, just know when it works and feel free to do that. Okay, so that's simplifying, right? Simplifying. So that should be able to get you deeper into your worksheet on your practice problems, because now we have find a counterexample, right? We have verify, plugging in actual numbers. And now we have kind of the seeds of what's going to constitute the mechanics of our proofs. We can simplify down to things. Okay. Any questions so far? 15 days left until graduation. Wow. We better boogie. All right. Simplifying expressions and or rewriting them in a more useful equivalent expression is also very helpful when you're trying to solve conditional equations that have trig in it. Okay. Conditional equations. What do we do with conditional equations? We solve them, right? So let's look at example 7. It says to find the solutions to 2 sine squared of x plus sine of x equals 1, such that A, your angles x are between 0 and 2 pi. That's going to be finding all the solutions within one positive rotation. That's our comfort zone. Part B, from 0 to 4 pi. So we want to go one more rotation on the unit circle. That would be the next set that's coterminal with the first set. And then look, then all of them from negative infinity to infinity. It's going to be impossible to list them, right? Because there's infinitely many coterminal angles. So if we start with A, I think we can answer B and C. But first of all, looking at this, do we want to draw a line down the middle and start manipulating both sides so that one side matches the other? No, because it's not always true, is it? That left side is not always equal to 1. It's not an identity. You'll know in advance if something is an identity or not. Okay, that takes a lot of frustration out of it. This one is a conditional equation. So it's only true for certain values of X. Your job is to find them. Okay, so what are we going to do? Well, I've got sine squared plus sine equals 1. Have you ever come across in another math class something to this effect where you have a squared variable term, a non-squared variable term, and a constant? Absolutely. But it probably wasn't in terms of sine, was it? It was probably just X, right? So if I replace sine of X with just X, this would look similar to this. 2x squared plus X equals 1, right? In other words, let X equal sine of X. How would you solve something like that? When you have a squared term, a non-squared term, and a constant, you get everything on one side, right? Set it equal to 0. 2x squared plus X minus 1 equals 0. And then you either try to factor it as the product of two binomials, or at the very least, you had the quadratic formula. Does this one factor? It's the fun one if it does, right? Factors of 2 and -1 that add up to 1. Well, we had a lot of practice with this earlier in the year. 2 is prime. So is 1. 1 has got to be 1 and 1. So it's got to be a 2x1, x1 combo if it's going to work at all. And all we got to worry about is the SIG and signs. So I want a positive middle term. So the larger product, which is the outside 2, needs to be positive. And I have a negative product, so that one needs to be negative. And then you just check. Do the inner and outer terms add up to give you positive 1? 2x minus 1x is 1x. Yeah, that works. All right. And then you would set them each equal to 0. You would say x equals 1/2 or x equals -1. And now you'd be done, right? You'd be done. That's why you learn to do this in Algebra 1 or Algebra 2 for sure, so that you can use this kind of template to do bigger and better things, right? So there's really no reason why we can't use that same idea for our actual problem. Let's do that. I'll use a different flavor here. How about green? I have a squared variable term, a non-squared variable term of the same type, and a constant. Let's get everything on one side and set it equal to 0. 2 sine squared of x plus sine of x minus 1 equals 0. Does it factor? Yeah, I think it does. It's going to factor as 2 sine of x minus 1 times 1 sine of x plus 1. And if you want to verify it, FOIL it back out. The first would be 2 sine times sine. That's 2 sine squared. Boom. The outer is 2 sine. The inner is minus sine. 2 sine minus sine is positive sine. And then the last is -1. So yeah, you can have things that have the quadratic form that aren't necessarily always just plain old boring x squared and x. You can have sine squared and sine. You could have cosine squared and cosine. You can even have the natural log squared and the natural log. You can have e to the x squared, which would be e to the 2x, and e to the 1x, okay? You could even have x to the 4th and x squared, x to the 100th and x to the 50th. As long as the smaller powered one is half the larger one, you could factor it as a quadratic. Pretty cool, right? Well, now we would set each of these equal to 0. So 2 sine of x minus 1 equals 0, and sine of x plus 1 equals 0. And we would solve for sine of x. So we get sine of x equals 1/2, or sine of x equals -1. Now notice that's the exact same thing we did over here, wasn't it? We got x equals 1/2 or x equals -1. The only thing is, when it was x, we were done. But x was really just a temporary position holder for sine of x. So now we're not quite done. Now there's one more fun, awesome step. Okay. I need to solve for x, which is an angle where sine is equal to a half from 0 to 2 pi. All of them. This is not the function anymore. This is just the operation. And then I need to find the angle x where the sine is -1 between 0 and 2 pi. All of them. So it's not unit circle time. It is time circle unit, right? We got to use it backwards. Yeah. So we got to take the inverse operation of both sides. So x is going to equal the inverse sine of a half, the operation, not the function, and x is going to equal the inverse sine or the arc sine of -1, the operation, not the function. Okay, we're solving an equation and we want all the solutions on part A between 0 and 2 pi, all of them. Okay, not just one. Okay, so let's think about it. Where is sine equal to a half? Well, the one that's in the PVR is probably the one that we're most comfortable finding now. It's in quadrant 1. It's what? Pi 6, right? So if we were doing just the function arc sine or inverse sine, that would be the only answer. But there's another angle between 0 and 2 pi where sine is a half. What quadrant is it in? 2, sine y height, and the reference angle is pi 6. So what's the pi 6 reference angle in quadrant 2? 5 pi 6, yeah. So that one little equation has two answers between 0 and 2 pi. And then let's see what this other one has. Inverse sine of -1. I think sine is only equal to -1 one time all the way around, right? Where is it? 3, yeah, 3 pi over 2. Good, 3 pi halves. So that's just one solution. Okay, so I'll write that down. So there's answer to part A. This equation up here between 0 and 2 pi, once around the unit circle, is only true under the conditions that the angle is one of those three. Got it? Boom. All right, so now we can answer part B. What are the solutions between 0 and 4 pi? Well, 0 and 4 pi covers all of the rotational angles from 0 to 2 pi. We just have to go one more rotation. So here's what it's going to be. From 0 to 4 pi, it's going to be x equals pi 6. And its coterminal buddy, one rotation away, x equals 5 pi 6. And its coterminal buddy, one rotation away, and x equals 3 pi halves, and its coterminal buddy, one rotation away. So notice I just left a little space behind each of these. So what would be the next coterminal angle that's one positive rotation away from 1 pi 6? Yeah, very good. One rotation, of course, is 2 pi, but in terms of 6, it's 12 pi 6. So all you got to do is add 12 pi 6 to pi 6, and you get 13 pi 6. All right, that's in the next rotation. If I had said between -2 pi and 2 pi, you would have subtracted 12 pi 6, right? Okay, and then we'll do the same thing. So we get 5 pi 6, and then its coterminal buddy, one rotation away. 12 plus 5 is 17 pi 6. And then we have the last guy, 3 pi halves. Now, in this case, one rotation is still 2 pi, but in terms of halves, it's 4 pi halves, right? So we just kind of cut the 2 pi up into however many partitions we need. So what's 4 plus 3? 7 pi halves. There you go. So within the first two rotations, there's 2, 4, 6 solutions, right? If there's 3 within one rotation, it's going to be twice as many within 2, 3 times as many within 3, et cetera, et cetera, et cetera. Now on part C, it says to find all the solutions from -infinity to infinity. Oof. Pi 6 is going to have infinitely many coterminal angles to it. 5 pi 6 is going to have infinitely many coterminal angles to it. And so is 3 pi halves. Infinity plus infinity plus infinity is how many? Infinity. Can we list them all? No. Not in the 15 days we have left until graduation, right? Nor the 15 years left until your 15 or 16-year reunion, right? So there's got to be a better way. We're not going to list them all. We're going to go ahead and say something, yeah, to that effect. Good. So here's what we're going to do for part C. We're going to take each of them. We're going to say x equals pi 6, And then underneath there, x equals 5 pi 6. And then underneath there, x equals 3 pi halves. Those are the main ombres within one positive rotation. And to list all of them, which is impossible, we're just going to do like the set builder notation. We're going to build a rule so that anyone who wants any other solutions can find them when they want. So it's going to be pi 6 plus all of its coterminal angles. Coterminal angles in this case are how far apart from each other? Multiples of 2 pi. So 2 pi n, where n is a what? It can't be a real number. It has to be a whole number that's either positive or negative. We call that the integers. Yeah. So that takes care of minus. You could say plus or minus if you want, but you don't have to, because if n is an integer, n could be -1, and that takes care of subtraction. N could be -2. And then we just do the same thing for the others. Plus 2 pi n, also where n is an element of z, and then 3 pi halves plus 2 pi n, where n is an element of the integers. Okay. So there's all of them. And of course, if you wanted to write this first, to answer part A, you would let n equal 0, right? To answer part B, you would have let n equal 0 and 1. Right? And if you wanted between 0 and 6 pi, you would let n equal 0, 1, and 2, so on and so forth. Right? So those, like if you were writing a computer program that would list as many angles as the user wanted, you would say specify the interval, and then you can calculate how many values of n that's going to be, and then the computer could just generate them with this, right? Some kind of nested loop. All right. Now, as fun as that was, did we even really use an identity on that one? Did we use any of the identities for that? No. So that was one of those solving a trig equation that I say we're just dipping our toe in the water. We're testing the waters, like, ooh, chili, right? Anyone ever stuck your toe in chili? Like, ooh, that's hot. Not on purpose. Not on purpose. Right. Yeah. You thought I was saying the water was chilly, but no, I was saying we're sticking our toe into chili. And now we're saying, ooh, beans. And this is how we get behind, right? Yeah. Okay. All right, let's move on to example 8. Find the solutions to cosine cubed of x over sine of x equaling cotangent of x. It's a conditional equation such that x is between -2 pi and 2 pi. And then it says, be careful not to lose any variable information in the process. Okay. If you lose variable information, you lose possible solutions. We've talked about that this year. So we don't want to divide out a variable from both sides. Now, what's our strategy if I want to find all of them between -2 pi and 2 pi? Well, my strategy is find all of them between 0 and 2 pi, which is our comfort zone, one positive rotation, and then I can subtract a rotation to get the others, right? So that's probably your best strategy each and every time. All right. Well, let's go ahead and rewrite this problem down here. Cosine cubed of x all over sine of x equaling cotangent of x. All right. Where to start, what to do, what's going to happen, how can I proceed? Well, here's what you don't want to do. Do not do this. Oh, I spelled donut. My bad. I'm thinking about pastries. Do not do this. Using an identity, you could say that this is cosine of x times cosine squared of x all over sine of x, right? In other words, split cosine cubed up into cosine times cosine squared. And then you could call this cotangent of x over here. By the associative property of multiplication, you can actually associate those two together like that now. What's another name for cosine over sine? Cotangent. So you could call that cotangent of x times cosine squared of x equaling cotangent of x. So far we haven't done anything wrong. There's no sin here. But now if you say, ooh, right? And you divide both sides by cotangent of x, It divides out from both sides, and we're left with cosine squared of x equals 1. If you were to proceed now and try and find the solutions to what remains, you will get part of the solution set, but potentially you will not get it all, because what happened to cotangent? Is it there anymore in the problem at all? No, it's not there at all. We lost it on the left side, which is usually okay, as long as it reappears in some form on the other side, but it didn't. We wiped it out. We lost it all. So that would be bad, bad, bad. Okay. We lose information. Lose info means you lose possible solutions. Don't do that. Now, what you could have done instead is pick back up from this line here. Cotangent of x times cosine squared of x equaling cotangent of x. A better strategy would be not to divide out the cotangent, but remember what we did on the previous problem. When you have more than one variable term, get everything on one side by subtracting cotangent of x and setting it equal to 0. Más mejor que bueno. And now, when anything is equal to 0 and we're trying to solve it, we should then next attempt to do what with it? Factor. Yeah. And the first rule of factoring is look for a common factor. Do we have a common factor? I spy a cotangent factor in both of them. So I will factor it out, and I'm left with cosine squared of x minus what? 0? Factoring out is dividing out. Anything divided by itself is 1. Okay. And now that it's factored, we could set each factor equal to 0. So here we go. We get cotangent of x equals 0, or cosine squared of x minus 1 equals 0, which if I were add 1 to both sides, I get cosine of squared equals 1. So notice what I said up here. If you would have proceeded to solve cosine squared equals 1, you would find part of the solution set, because notice that little factor group still shows up. But what else possibly can generate solutions? Cotangent of x equaling 0. And when it's gone, you can't use it. All right, so let's go ahead and solve this now. This is why we have to know the unit circle so well. It is not unit circle time, it is time circle unit. We got to use the unit circle backwards. Where between 0 and 2 pi, we'll always find it between 0 and 2 pi first. Where between 0 and 2 pi is cotangent equal to 0. If you want to come off to the side and call it theta instead of x, cotangent is x over y. Yeah. So on the unit circle, this is thinking in the unit circle, cotangent is 0 when x is 0. Cotangent of 0 is undefined. Cotangent of pi is undefined. If you remember the graph of cotangent, it has a vertical asymptote at 0, pi, 2 pi, 3 pi. So again, when you think of the unit circle, más mejor que bueno sí, otra vez, when x is 0 on the unit circle, that's when we're on the y-axis, right? And on the y-axis, that's pi halves and 3 pi halves. So this is going to be x equals pi halves and 3 pi halves. Those are the two within one positive rotation. Okay. And now, if you want to put this over here, that's from 0 to 2 pi, colon. What would I do if I wanted to get the ones from negative 2 pi to 0? That's one rotation away. I just got to back up a rotation, right? So instead of adding a full rotation, I just have to subtract the rotation. So that's going to be pi halves minus 2 pi, which is 4 pi halves. And of course, that's going to equal what? Negative 3 pi halves. And then x equals 3 pi halves minus the full rotation. And that gives you negative pi halves. So those are the 4 solutions. But that one piece generates that we would have lost if we had divided it out. Okay, now that was just one of the pieces. Look at this. The fun is not over. It's bless you. It's like bless you. We spent the whole day at Disney World in our favorite park. And now we get a bonus day. We're back in again. And we can go back to the same park or we can go to another one, right? I say Disney World because there's 4 parks, right? Plus 2 water parks. How are we going to solve cosine squared equals 1? I first need to solve for cosine of x. How do I unsquare a conditional equation? What's the inverse of squaring something? Square rooting it. So if I take the square root of this side, I got to do plus or minus the square root of the other side. You don't have to do plus or minus on the variable side, but on the numeric side, you do plus or minus. All right, so I'm going to get cosine of x equals -1 or cosine of x equals +1. What the heck? This one equation generates 2 more equations? Yeah, that's right, buddy. And now let's go ahead and solve for x. You don't have to show me that you're taking the inverse cosine of both sides. Okay, you can if you want. But let's go ahead and solve for x between 0 and 2 pi, our wheelhouse, okay, our comfort zone. So I'll put 0 to 2 pi colon. Where is cosine equal to -1? Cosine of what angle gives us -1? Cake? Pi. Yeah. And then that's it, right? And then over here, where is cosine equal to +1? 0 and 2 pi, right? So we could say 0. Now 2 pi technically would be the start of the next rotation, but I'm going to go ahead and list it because I wanted all the solutions on the closed interval, right? From 0 to 2 pi. So I do want both of those, okay? So that's 3 solutions now. But there's more because I have the expanded interval, right? How do I find the ones from -2 pi to 0? Instead of adding a full rotation, like previously we went to 4 pi, I just got to what? Subtract. So we're going to get pi minus a rotation, which is 2 pi. So that gives us -pi. And now I have x equals 0 minus a full rotation. So that gives me -2 pi. And then I have 2 pi minus a full rotation, which gives me 0. Oh, but did I already have 0? Yeah, this is a duplicate. Okay. So let's corral these loose dogies, right? I have pi, 2 pi, 0, -pi, -2 pi. So all of the solutions that I have highlighted are now solutions because, bless you, there's so many of them and they're all over the place. Let's put these dogies, these beeves into a corral. So the solution set is going to be x epsilon, and we'll put braces, and we could just list them now like a roster. Pi halves, comma, 3 pi halves, comma, -3 pi halves, comma, -pi halves, comma, pi, comma, -pi, comma, 0, comma, 2 pi, comma, -2 pi, comma, chameleon. Oh yeah, culture club. Yeah. Do all of those work? How do we know if all of those actually work? Either A, we trust our math. Did we make any mistakes along the way? As y'all are my witness? Because if we did, it's on y'all too, not just me. It takes a village to solve a trig problem up until the day of the test, then it's just you. What if we had doubts? What if we were concerned that some of these actually did or did not work? Is there a way to test them back out? Yeah, you can check your work. That's a good thing about math by plugging them back into the original equation. Now, that's important because while the previous problem was just plain old sine squared and sine and no denominators with a variable, those are continuous for all real numbers. What do you notice about our original function? It had a sine of x in the denominator, right? Now, sine of x has the domain of all real numbers, but there are certain values of sine of x that give us a 0, yes? And if sine of x gives us a 0 and we plugged it back into the original, we would be dividing by 0, wouldn't we? Can we divide by 0? No. Are we Chuck Norris? No. Are we Isaac Newton? No. Therefore, we can't divide by 0. Also, cotangent has discontinuities. It's cosine over sine. So it's also undefined when sine is 0. So, whenever you have denominators with variables, you might get some impastas trying to sneak in to the solution set, right? We better go back through and weed some of these out. If I plug in any of these angles, do I get a 0? Because if so, I'm the bouncer at club solution. You kick them out. What's sine of pi have? 0 or not 0? It's 1, right? So congratulations, you can stay. Have a good time. Sine of 3 pi halves? It's not 0. It's -1. You need to change your attitude, buddy. We don't like negative attitudes, but you can stay in the club, right? Sine of -3 pi halves? That's 1. That's coterminal with pi halves. Welcome to the club. Sine of negative pi halves? Coterminal with 3 pi halves. You're in. Those guys were dancing on the dance floor. But now we go into the recesses of the club, into the corners, into the bathroom stalls where people are hiding out because they don't want to be found. Hi! I know you're in there. What's sine of pi? 0. Get out of here. Just flush, I guess. Flushing down the commode. It's either a giant commode or pi is kind of small enough to fit through the commode, right? The analogy's breaking down. I better abandon it. What's sine of negative pi? 0. What's sine of 0? What's sine of 2 pi? What's sine of -2 pi? Holy moly. Good thing we kind of snuffed them out. There was more of them than the other guys. They would have taken over the club, right? Yeah. That's something that you always want to consider. How would you know to do that? I just told you, right? How would we know to look for it then? We start with a conditional equation and we have a variable in the denominator. We spent quite a lot of time talking about domains of algebraic functions, right? Can't divide by 0, can't take square root of negative. It works for trig as well. So if you would have spotted that from the beginning, right? Take inventory, like don't even let these guys in to begin with. Just say, if sine of x equals 0, you know, which is going to be at x equals 0, pi, 2 pi, so on, and 3/4, whatever. Like you have that picture of them at the door and you're the bouncer, you're like, nope, can't even get in here, right? Don't even let them in. Or you let them in and you check your answers on the back end and then you toss them out. Is it more fun being a bouncer if you refuse someone to get in? Or is it more fun as a bouncer if you let them in and then you get to throw them out? Second, yeah. I guess it feels better. Like I bounced them off the pavement, boom, 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 right? I don't know. Is that why they're called bouncers? It's not because they just hop around to the music while they're working, right? Jump around, jump around. They'd be called jumpers, right? No, bouncers. Bounce around, bounce around, bounce up, and get down. And that's how we get behind. All right. Now, is that the only way to do that problem? Is that the only way to do that problem? The answer is no. Let me show you another way to do that problem. You could have, from the very beginning, gotten everything on one side and set it equal to 0. Minus cotangent of x equals 0. Now, this is the way that I would prefer. Okay, so why'd you do it the other way first, sir? Because that's how we were rolling, right? It worked. This is how we would do this if this were like a calculus class, all right? We need to find solutions to conditional equations all the time, especially when we have trig. You might have learned in your algebra class to like multiply both sides by sine of x, okay, or whatever, clear out the denominators. But that kind of changes the composition of the problem. What we're going to do is get everything on one side, set it equal to 0, And now, kind of like we were trying to simplify down to a single power of a single trig function, how do I get two terms into one term if at least one of them is a fraction? I need a what? A common denominator. Now, you could put that, you could put that over 1 and then multiply by sine over sine. That would definitely work. But there's another way to do it. Another strategy comes into play. Everything is already in terms of sine and cosine except for that dude. So let's call it cosine over sine. And that kills two birds with one stone, right? There's a plethora of birds and a dearth of stones. Why did that kill two birds with one stone or solve two problems at once? It gave me a common denominator, right? And it put it in terms of sine and cosine. So now I'll just put it all over the common denominator. And that's cosine cubed of x minus cosine of x. Once you have a single fraction equal to 0, this is money. Let me go to green right here. Money. This is your money step. You know why? When you have a single fraction equal to 0, because it's easier to solve now. Okay. When we get to calculus, we're going to be interested in where this thing is 0 and where it's undefined. A fraction is equal to 0 when the numerator only is equal to 0, and a fraction is undefined when the denominator only is 0. So from here, we're at a fork in the road. Later on, we're going to set both the top and bottom equal to 0. Okay, setting the bottom equal to 0 is effectively finding the domain. Now, here's what we're going to do. A single fraction is equal to 0 when the numerator is equal to 0. Okay, so again, we're going to say when, and we're going to set the numerator equal to 0. Now, it has the same algebraic feel as multiplying both sides by sine of x. But I told you we don't want to do that because if you multiply both sides by sine of x, what happens to sine of x? It's gone, right? Completely from the problem. And when you lose variable information, you lose possible solutions or you lose possible restrictions, right? You might let the bad guys in. All right, so we say when and we set the numerator equal to 0. Now we have the numerator equal to 0. Now we try to factor it. What's the first rule of factoring? Panic? No, keep your lizard brain at bay. Use your cerebral cortex. Guilford will tell you that if you start panicking, if you let your amygdala fire up, your cerebral cortex is literally physiologically cut off and you can't do higher order thinking. The lizard brain takes over and that's fight or flight. So keep that in mind when you're doing anything like AP exams this week or next. Let's pull out a cosine of x here, right? And what are we left with? We're left with cosine squared minus 1. And now we can set both equal to 0. So cosine of x equals 0 or cosine squared of x equals 1. Go ahead and do that if you want. I abandoned it temporarily, okay? I said that a fraction is equal to 0 when the numerator is 0, right? Only. 0 divided by 5 is 0. 0 divided by 10 is 0. So I know the sign is still there. It's going to affect the domain. I don't want to divide by 0, but that fraction is only 0 when the numerator is 0. Okay, Simone, it's kind of like doing this, but I don't want you to think about it this way. It's kind of like multiplying both sides by sine of x, right? And it would divide out here, and then we get 0 times sine, and we get the same result, but it's not the same idea. Okay, so we do it this way. And now cosine is equal to 0 at pi halves and 3 pi halves. And of course, if you subtract 2 pi from each of those, you get negative pi halves and negative 3 pi halves. And over here, when I take the square root, I get cosine of x equals 1 or cosine of x equals negative 1. And of course, that's going to give us 0, pi, 2 pi, negative pi, and negative 2 pi. But here's the deal. Because we did not divide out the sine of x, or we know that sine of x can't be 0, we actually toss those out, okay? And we still get the same solution set, all right? So it's a slightly different philosophy on how to solve fractional equations when they're equal to 0, all right? And that one did use an identity. We did it two different ways, right? We did it two different ways. And both of them work as long as you remember not to divide by 0. Okay, so we didn't finish, but we will finish tomorrow. Tomorrow's being Friday. Yeah, I said Friday. And that means your worksheet's going to be due Monday at 9 a.m. Okay, 9 a.m. Comments or questions? Enjoy the rest of Adele's birthday today. Maybe text her and say, happy birthday, Adele. In my opinion, you should have had it all.